AL. And this is the expression that gives you the self-inductance of a solenoid. An example. Find the self-inductance of a 600 turn solenoid of length 12 centimeter and area 5 centimeter square. Well, we have the length, we have n the number of turns per unit length, which is n over L, which you can calculate, and we got area is 5 centimeters squared, and convert that to square meter. And L, the self-inductance of a solenoid, is mu 0 n squared AL, and we have all those quantities. We replace those quantities by the values. That gives you 1.88 times 10 to the negative 3 Henry. Well, in fact, a coil like this has a self-inductance value. This is actually a solenoid. An inductor is normally a coil wound in the form of a solenoid, and its self-inductance is mu 0 n squared AL, where n, small n, is the number of turns per unit length, and of course A is the area of cross-section. How about energy of an inductor? An inductor stores energy, does it? Well, just like a capacitor, an inductor stores energy in an electrical circuit. It can be shown by simple considerations that an inductor of inductance L carrying a current I has a stored potential energy given by Um. The potential energy of the inductor is 1/2 Li squared. Now, magnetic energy of a solenoid can be written as Um equal to 1/2 mu 0 n squared AL. What does that quantity give you? Mu 0 n squared AL is the self-inductance times I squared, or we can write it as 1/2 mu 0 n squared I squared times AL. What does AL represent? A is the area of cross-section. A is the area of cross-section, and L is the length. So what does that quantity represent? Well, AL is the volume of the solenoid. So energy density of a solenoid is a measure of its energy per unit volume. So what is the energy per unit volume here? If you divide this energy by this volume, you get energy per unit volume, and that will be 1/2 mu 0 n squared I squared. That's a measure of the energy per unit volume of the solenoid. And we can write it as 1/2 mu 0 times mu 0 squared n squared I squared. Did you see how that can be written like this? What all I did is to multiply by mu 0 and divide by mu 0. Why did I do that? What is this quantity? What is mu 0 Ni? Mu 0 Ni is the magnetic field inside the solenoid. So mu 0 squared n squared I squared is simply B squared. So it can be written as B squared over 2 mu 0. And what is this? The energy density, the energy per unit volume of a solenoid. In fact, when you say a solenoid, you're talking about an inductor of this type. So an inductor in the form of a solenoid has an energy density given by 1/2 B squared over mu 0, or B squared over 2 mu 0. An example. A toroid of mean radius 25 centimeter and circular cross-section of radius 2 centimeter is wound with a superconducting wire of 1000 meter that carries a current of 400 ampere. What is the number of turns of the coil? What is the magnetic field at the mean radius? Assuming that B is a constant over the area of the coil, calculate the magnetic energy density and the total energy stored in the toroid. Now, what is a toroid? If you look at an inflated tire, it's actually a toroid. It has an inner radius and an outer radius. Here, the inner radius is A and the outer radius is B, and the average radius indicated by these blue lines is R. Alright. First of all, the cross-sectional radius is 0.25 meter. What does that mean, cross-sectional radius? If you cut the toroid at anywhere, the cross-sectional radius, that is that radius, is what is given to us. Therefore, the length of one turn. Now, look at these turns. Now, if you take one turn, that is a circle of radius this. Therefore, the length of one turn will be the circumference of that circle. 2 pi r, 2 pi times that radius, and that is the length of one turn. Now, the number of turns is total length divided by the length of one turn. Is that right? If you take the total length of the toroid and divide it by the length of one turn, that will give you the number of turns. So, the total length is not the total length of the toroid. The total length is, if you stretch the whole wire, and that will be the total length. That total length divided by the length of one turn will give you the number of turns. So the total length is given to be 100 meter. The length of one turn we just calculated, and that gives you 7,958 is the number of turns of the toroid. The magnetic field at the mean radius. Well, the mean radius will be over here, is that right? What's the expression for the magnetic field? Is mu 0 Ni over 2 pi r. And that will be mu 0 Ni. Mu 0 is 4 pi times 10 to the negative 7. N is the total number of turns, that is... Now, remember, don't confuse between lowercase n and uppercase n. The uppercase n is the total number of turns. So that will be, and the current and 2 pi r. This is a measure of the magnetic field at the mean radius of the toroid. And that will be 2.55 Tesla. What's the next thing? Assuming that B is constant over the area of the coil, that is, if you take the area of the coil anywhere, assuming that B is a constant there, calculate the magnetic energy density. Alright? The magnetic energy density can be calculated as, you know that equation, B squared over 2 mu 0. We just calculated B. So we can use that to calculate the magnetic energy density. And that will be 2.58 times 10 to the 6 joules per meter cube, energy per unit volume. And the total length of the toroid is 2 pi times the mean radius. That is 2 pi times, that's the mean radius, 2.25 meter. And the area of cross-section is pi r squared. Therefore, the volume of the toroid is area of cross-section multiplied by the length, isn't it? We know the total length of the toroid and the area of cross-section. If you multiply that area of cross-section by that length, we get the volume V. And the energy stored in the toroid is V times energy per unit volume. Is that right? We just calculated the energy per unit volume, and if you multiply that value with the volume of the toroid, that will give you the total energy stored in the toroid. So that will be the volume of the toroid, that's this quantity, times energy per unit volume, and that is 5093 joules is the total energy stored in the toroid. Well, that is the end of that lesson, and in the next lesson we will be looking at alternating current, how to generate it, and what are some of the properties of alternating currents.